so we can basically see the other broader audience other than our university, basically.
That's great. That's great. Thank you.
Thank you.
So we have 1 hour, I guess, probably 45 or 50 minutes of presentation and 10 minutes of question and answer.
Right. Yes. Yes. So if you can please have it in a high level in 45, 50 minutes, and then we will basically have some questions at the end.
Okay. Yeah, sure. Of course.
Thank you. So we will give, if you don't mind, a few more minutes, and then we will start.
Sure. Sure.
Amir, how is the weather in Memphis? Here is a snow. You can't believe it's like a snowy. I would say even 2-3 inch of snow is already on the ground.
No, it's great. It's just hot.
Oh, really? No.
Yeah, we're using our AC in home, and I'm enjoying the weather. You know, after 10 years of snow in Canada.
That's good. That's good. No, here is unusually snowy today.
Okay. And still everything is locked down. Is that right?
Everything is locked down, and we have no access to lab. What about you guys? Do you guys have like teaching in summer as online remote teaching, or
yeah. So all of the classes are supposed to be online in summer. For the fall, we have not decided yet. Who knows? But we are planning to. I mean, we assume that those courses during fall will be online. So we are preparing ourselves to deliver all the courses online.
Yeah, I guess pretty much like us. Pretty much like.
Yeah. And that's a big problem for labs. Sorry.
No, sorry. You know, I think everybody is listening and they're anxiously waiting for your presentation.
Great.
So I would like to go ahead and start. Hi, everyone, again. Thanks for joining this seminar in this at the University of Toledo. Today's speaker is from the University of Memphis, Dr. Amir Hadadzadeh. Processing microstructure property relations in advanced metal and alloys, multi-scale characterization. His PhD interesting this.
Hi everyone, I'm very happy today to talk to you and share some. I hope everything goes and you enjoy. So as I talk about the role of that kind of microstructures on the mechanical properties. So in this talk, briefly, I will go through my research background and my research approach and the importance of the research that I'm doing. And I will go through some of the highlights, starting with hierarchical microstructure in SLM, ALSI, 10MG, alloy and the effect of such a kind of microstructure on the mechanical behavior, both quasi-static and dynamic loading conditions. And if I have time, I will go to another example or another case study on emerging stainless steel, and then going to the concluding remarks. So as Dr. Sujudi mentioned, I'm currently an assistant professor at the Department of Mechanical Engineering, University of Memphis. Before that, I was a postdoctoral fellow at Marine Additive Manufacturing Center of Excellence at the University of New Brunswick in Canada. And meanwhile, I was a visiting researcher at Canmet Materials, which is a national lab in Canada. And prior to that, I was a postdoc research associate and also PhD students at the University of Waterloo in Canada. So in MAMC, the Marine Additive Manufacturing Center of Excellence, we had a pretty big research group, and we were engaged in broad research, collaborative research with different universities coast to coast in Canada. So New Brunswick is here, and the Canmet material was located in Hamilton, close to Toronto. So I spent most of my time in Ontario rather than New Brunswick. And the reason that it was in Canmet Materials was using their state-of-the-art research facility, including EBSC and TEM machine. And this picture was taken during summer. I guess now they still have snow on the ground, and it was pretty cold, similar to your weather. So in terms of my research approach, my background is in material science and engineering, and I'm really interested in the material science paradigm, or tetrahedron, where we have 4 vertices: processing, structure, properties, and performance. And it's very well known. I'm quite sure you have seen that before, or in any material science textbook. If you open that, the text will start with this tetrahedron. So everything in terms of properties of a material is affected by the structure, and structure is determined by the processing. So it's very important to have a knowledge on that. And in the case of additive manufacturing, for sure, processing is additive manufacturing. And what I'm doing is characterization and modeling. So I'm in the middle of this tetrahedron. I characterize the structure at different length scales to understand what is going on in the structure of the material, how the process has affected that, and how that structure will determine the properties. And today I'm going to talk about my research at MAMC during that 2 years of postdoc. So in MAMC, I was engaged in a couple of research projects on different types of materials, including aluminum alloys. AlSi10mg is the probably most common material for selective laser melting, which is a kind of additive manufacturing. Also, another type of metallic material, marrying stainless steel CX. Nickel aluminum bronze, which is a copper-based alloy Ti6 for marrying steel, and stainless steel 316L. So a variety of materials, and in all of them, I was interested to explore the hierarchical microstructure. And again, if you go to the literature related to additive manufacturing of metallic materials, in most of them, you will see this term, hierarchical microstructure. So it means at different length scales, we have different features. So I'm exploring those features. And I'm trying to understand the effect of those features on the deformation behavior of the material and the role that they are playing in terms of the strengthening of the material, and also their effect on high temperature behavior of AM materials. We started a research back in Canada, and still I'm interested in that research, hopefully to continue that. And the outcome of this research, by understanding the effect of the processing on the structure of the material and how microstructure will enhance the properties, the outcome will be designing and developing advanced AM alloys with superior mechanical properties. We can also study other types of properties in the materials, like corrosion properties, physical properties, and so on and so forth, and try to correlate those properties to the microstructure as well. So I'm pretty sure most of you are familiar with additive manufacturing. In additive manufacturing, we build a three-dimensional part by joining feedstock material on top of each other in a layer by layer manner. So we, in many cases, specifically for metallic materials, we melt and join those layers on top of each other. We usually use a high power energy source, and based on the ASTM standard, we have, in general, we have two types of metal AM technologies. We either have powder bed fusion, PBF, or directed energy deposition, DED. And depending on the type of the power energy source that we are using, we either have a laser beam or an electron beam. And the process that use laser beam is called SLM or DMLS, selective laser melting. And most of my research is around here. I've done some research on EBM and DED as well, but today I'm going to talk about only SLM. So in SLM, I'm not sure whether if I played the movie, hopefully you can see it. But in SLM, again, I'm quite sure you know that we have a bed of powder, and a laser beam will melt layers of material, and by adding powder on top of each other, we just build a component layer by layer. So there are many advantages in terms of using additive manufacturing. For example, we can have on-demand fabrication. We can fabricate complex parts in just one step of process, and many other advantages, as you know. But besides that, there is another aspect here, and that's the properties of the component that we are obtaining. It's not just about making a complex shape component. We should ensure that the final properties are desirable. So there are two perspectives in studying the properties, or specifically the mechanical properties of SLM component. We either study them based on the structural integrity or from material science. When we say structural integrity, means we are trying to eliminate different types of defects that can form in the material, like porosities and holes in the sample, cracks like this case. Also, the surface roughness is another problem in SLM materials, and we're trying to, because again, SLM is supposed to fabricate near net shape components. So if we find a way to reduce the surface roughness, it's good for some specific applications, specifically when we have fatigue. Because for fatigue, a rough surface is not a good option. And also another aspect is reducing the other types of defects like inclusions. So by reducing those defects and controlling controlling them, we can ensure structural integrity to have a strong component. But another point of view here, which I'm interested in, is studying the material from a material science point of view. To look at the microstructure of the material, to see how that microstructure at different length scales, from atomic scale, as you see here, up to sub-millimeter scale, how these features will affect the properties. So I start with a case study here about development of hierarchical microstructure in SLM ALSI technology. In ALSI technology is the most common aluminum alloy used for selective laser melting, because the composition of this alloy is close to the eutectic composition of aluminum silicon system. So we have a narrow range of solidification, which is pretty helpful in terms of making a component without any significant defect. So in this study, we fabricated two types of samples, two rod-shaped samples based on their orientation with respect to the building direction. We called them horizontal sample and vertical sample. So in the horizontal sample, as you see here, so the geometry of both samples was the same, but for the horizontal sample, the longitudinal axis of the sample was perpendicular to the building direction. And for the vertical sample, the longitudinal axis was parallel to the building direction. And we started characterization, and any metallic material that you start to characterize, you start most probably with optical microscopy. So I did the same thing, and here from optical microscopy we just can see a general structure of the material. So this is the side view. So z-axis shows the building direction. So we are looking to both samples from side view. We just can see the overlap melt pools. So these are the melt pool boundaries, for example here. And this type of structure is called fish scale structure, because we can see kind of fish scale from side view. And some other features which cannot be explored by optical microscopy. So I moved to scanning electron microscopy to see more details of the structure. And here we can see the so-called cell structure of the material. So cell structure is developed because of solidification. We have solidification during the process. We have a liquid material, and that liquid material solidified once the laser leaves the melt pool. And because of the high cooling rate, the microstructure is very fine. So the cell structure is now revealed here. And in this type of structure, we have an aluminum matrix. So these dark regions are aluminum matrix. And they're bounded with eutectic silicon walls. The brighter area is the eutectic silicon walls. And if you consider the scale bars that I'm using here, 5 micron, and in lower scale 10 micron, we can get an idea regarding the scale of these cells. Then we conducted, I conducted EBS, the electron backscatter diffraction. In electron backscatter diffraction, now we can study the grains. And in the context of additive manufacturing of metallic materials, there is a difference between the cell structure and grain structure. And first of all, with EBSC, we can study both the grain morphology and also the orientation of the grains or micro texture. The other feature here is the scale bar of the scale of the structure. So 100 micron. In the previous slide, the scale bar was 5 micron, and here is 100 micron. So there is a change in the length scale when we are studying cell structure and grain structure. The grain structure of both samples, more or less, is consisted of columnar grains. So these grains, as you see here, they're columnar grains. They are or they have developed along the building direction because of the direction of the heat transfer. The horizontal sample, we also have the same thing. So on the left-hand side, we have the vertical sample. Here on the right, we have the horizontal sample. More or less, we have kind of bimodal grain structure, both equiax and columnar structures. I don't want to go to details of such kind of grain structure evolution. If you're interested in our paper, I have used a solidification model to show why we have such a kind of grain structure and why we have a transition from such a kind of structure, from a columnar structure to more or less equiax structure, but changing the build direction. Now let's study the grains and cells in terms of their size. So again, since we are dealing with columnar grains, instead of quantifying them in terms of the grain diameter, I quantify them based on their major axis and minor axis. So in each columnar grain, I feed an ellipse to the grain and measure the major and minor axis. So the major axis is changing from about 2 micron, as you see on the graph on the left, up to about 17 micron. And the minor axis, this is for the case of horizontal sample, from about half micron up to 16 micron. And if we quantify the cell structure, we see that the cell size is changing from 0.4 to 1.2 micron. So this is the first step of understanding the hierarchy in microstructure. Grain structure and cell structure, there's at least one order of magnitude in terms of the difference in the length scale. So it means each grain is consistent of several cells, and we confirm that by TEM studies. So we study the sample by TEM, and this microstructure here shows the TEM structure in 011 zone axis of the aluminum, and the red dashed line shows the grain boundary, and inside each grain we see several cells. That's why we see such a kind of difference in the grain size and cell size. Now let's take a closer look to the structure of the material using TEM. So far, we explored the cell structure and grain structure. Now let's take a closer look to the other features. So here you see the STEM or scanning mode of TEM microstructure, and the EDS elemental maps are superimposed to the STEM microstructures. The red region shows the silicon. So those walls or the boundary of the cells are eutectic silicon walls, as for example, we can see them here and here. So these are eutectic silicon walls, and inside the aluminum matrix, we see two more features. First one is the tiny nanoscale silicon particles. For example, here in this picture, in all of them, we can see them. So we see many nano-sized silicon particles, and this scale is 400 nanometer. In addition to that, we see a network of dislocations. So these lines here in the structure, these dark lines in all of them are representing the dislocations. And that network of dislocation is called pre-existing dislocation network, which is a common feature in AM materials because we have a rapid solidification, we will have evolution of residual stresses, and because of those residual stresses, these dislocations will evolve in the structure. And these dislocations are interacting with the silicon precipitates. For example, here we can see some details. They're interacting with them, and also the eutectic silicon walls. For example, here the dislocations are interacting with the eutectic silicon walls. I studied the silicon precipitates using high-resolution TEM, and we can see the atomic structure, and there is a crystallographic relationship between the aluminum matrix and silicons, as you see in this graph or in this picture here. Another way to study the precipitates is using atom probe tomography. So in APT technique, we can study the chemistry of a material atom by atom. And here, in the case of the vertical sample, on top of the sample, this is a separate study, but it's quite interesting in terms of analyzing the microstructure consistency in AM material. So if we have a long sample, like the vertical row, from bottom to top of the sample, the material will experience different thermal histories. At the bottom of the sample, we have more repeated thermal cycles experienced by the material because the heat transfer direction is from the top layers to the bottom layers. That's why we see a difference in terms of the structure or the morphology and characteristics of the precipitates. Here in the top of the sample, we see large silicon precipitates and very tiny magnesium-rich precipitates. By moving to the bottom of the sample, those silicon precipitates start to dissolve because these silicon particles are not a stable phase in this system, because in aluminum silicon phase diagram, we don't have silicon precipitates or particles. These precipitates or particles develop because of the supersaturated aluminum matrix, because the silicon didn't have enough time to diffuse from the matrix to the eutectic wall. And that will affect the precipitate characteristics. So here on the top, we have a fully coherent precipitate with the matrix. Over the interface, we have probably a couple of dislocations because of the mismatch between the precipitate and the matrix. But at the bottom of the precipitate, as you see here, more dislocations evolve in the structure because of the mismatch. So far in the ALS technology material, I was able to show the hierarchy in the structure. Again, we have silicon precipitates. Their size is 62 nanometer. We have cell wall thickness, again, with this size, 0.126 micron. We have cell size or cell structure and grain structure with different size. And again, as you see here, the features in the microstructure of ALS 10MG are spanning almost 3 orders of magnitude or 3 length scale, from nanometer scale up to sub-millimeter scale over here. So that's the general picture in terms of the hierarchical microstructure in AM materials, in this case, SLM, AM, SLM. But there is a question here regarding the effect of hierarchical microstructure on the mechanical properties. So far we explored that, but the big question is, does this microstructure affect or control the mechanical properties? And obviously the answer is yes. So we did quasi-static tensile tests on those samples, vertical and horizontal samples, and we see the results here. And we compared the results to a die-cast counterpart. The same material fabricated through die-cast. So for die-cast material, the yield strength and elongation of the material are over here. But in our case, for our material, by changing the process to additive manufacturing, we were able to enhance both yield strength and elongation, as you see here. So I believe that this enhancement in both elongation and yield strength, which is unique in metallic materials, is coming from the type of the structure that we have. So I started to look at the structure after the formation. In both cases, again, here we see the stem images, the TM images in the scanning mode, along with the EDS maps, in this case, aluminum and silicon. So the density of dislocations has increased. And this is normal because during plastic deformation, we have motion of dislocations and generation of new dislocations. This is very basic in metallic materials. So these dislocations, as you see, for example, in this case, in here, we have a higher density, and we have measured that, a higher density of dislocations, and these dislocations, again, are hindered by the eutectic silicon balls. For example, in this case, we have higher density of dislocations close to the eutectic wall. So those eutectic walls are acting as barriers against dislocation motion. So they are playing a role in terms of a strengthening mechanism. I was also able to see the effect of silicon precipitates on the movement of dislocations. So here, for example, in this case, a dislocation, this dislocation is pinned by the silicon precipitates. This is a kind of classic image. Another case, a dislocation which is pinned by a silicon precipitates. If the dislocations are able to bypass the precipitates, like this case here, we see the effect of that. So this dislocation has gone toward the silicon precipitates after bypassing. And also there are some other dislocations that are still pinned by the precipitates. So precipitates are playing a role on the strengthening of the material because, again, they are hindering the motion of the dislocations. Considering these effects, we can use the fundamentals of alloy hardening to study the strength of the material. So as I mentioned, the eutectic silicon walls are acting as barriers against the dislocation motion. So they act like grain boundaries. So their role is similar to the Hall patch effect. We have silicon precipitates. They can act as O1 strengthening mechanism, and we have the pre-existing dislocation network. So we have dislocation hardening as well, because in presence of other dislocation, there is an interaction, in most cases, a repulsive interaction between dislocations. So we have more hardening in the material. Considering that, I don't want to go through all the details of the math here. I was able to predict the yield strength. Also, I measured the yield strength through the experiments, and there is a very good agreement between the measured values and the calculated ones, specifically for the case of vertical alley. As you see, 215 was predicted, and the measured value was 210 ampere, pretty close. But there is a slight difference between the yield strength of the in the case of horizontal sample. Sorry, I see some chats here. I'm not sure. We have to.
No, please go ahead. We are trying to make sure that we get all the questions answered.
Okay.
There was some confusion we figured out, and I'll basically interrupt and ask it. Thank you.
Okay, thanks.
Sorry.
Thanks. Yeah. So for the case of horizontal sample, there is a difference between the measured and predicted value, 222 MPa and 235 MPa. The difference between these two values is about 13 MPa in this case. And if we can look at the strength increment coming from these locations, is 17 and 14 MPa. So this 13 MPa is in the range of strength increment coming from these locations. So it's somehow significant. To address
Dr. Hadadzadeh, if you don't mind, I got a couple of questions. One of them just came late, so perhaps we're gonna for the end of the presentation, but one perhaps could be related to a recent topic. So from Pavan, so he asked that question, how do we eliminate defects like impurities, cracks, or undesired surface roughnesses in the SLM method?
Okay, that's a good question. Those defects usually they are eliminated by controlling the process parameters or developing optimum process parameters. For SLM material, the process parameters are well developed, very established. If you look at the papers published in 2013, you can see that there are a couple of good papers on studying the effect of process parameters on, for example, void formation or positive formation or crack formation for this material. But now each company, each provider will give you the proper process parameters to make sure that we don't have those kind of defects. Inclusions, we need to make sure that we have a high quality powder where we don't have any impurity in the powder to make sure inclusions will not form. For the surface roughness, again, by using proper process parameters, we can eliminate them. Residual stresses, process parameters, and probably post-process heat treatment. So at least for SLM materials, most of those defects can be controlled by controlling the process parameters. I hope I've addressed the question.
I will basically ask if there's a follow-up. Please go ahead. Thank you.
Okay. So I continue. To address this difference between the predicted value and measured value for the horizontal sample, again, we took a closer look to the structure of the material using TEM, and I was able to find traces of Mg2Si precipitates in this material. So again, this is a deformed structure. We see the interaction of over here, the bright field shows the deformed structure and the interaction of precipitates or dislocations with the features. And one of these features is Mg2Si, as you see them here. And also we're able to confirm that by EDS. 8 nanometer, this scale is 8 nanometer, and this kind of map is very unique because it's very difficult to obtain such kind of map at this scale using TEM. So MG2SI in some cases can play a role in strength of the material. I jump to the next part, which is dynamic or impact loading. So after doing quasi-static tests on the material, I also did some dynamic or impact loading, high strain rate deformation on the sample. And I chose the horizontal rod, as you see here. Some cylindrical samples were machined out from that rod, and by using the split Hopkinson pressure bar, we conducted high strain rate deformation on the material at different strain rates. So here, stress versus strain at different strain rates from 800 per second up to 3200 per second. So there are two deformation regimes. The top graph shows the material behavior under high strain rates deformation. In these three cases, 800, 1200, 1400 per second, we see an initial hardening in the material up to a peak flow stress. Here is the peak flow stress. And then after that, once we stop the test, we have a softening. This softening is not related to the behavior of the material. This softening is due to reduction in the strain rate because we deform the material and we stop it. So during deceleration of the angles, we have such kind of drop in the stress. But in the bottom graphs, we see a different behavior. So after that initial hardening and reaching the first peak flow stress, now we have a softening in the material. So this softening regime in the material is observed, which is followed by the second hardening regime up to the second peak flow stress. So these two different types of material behavior. Again, to study that, I used the same hardening fundamentals, Hall patch, plane roll, horizontal, and dislocation. And now we have another component, which is the strength increment due to strain rates. And there is a kind of a semi-empirical equation for that in literature to correlate the increase in the strength of the material because of strain rate to the level of strain rate, and A and M are materials constant. On the right hand side, I have shown the effect of strain rate on the strength of the material, both yield strength and the peak flow stress for different strain rates. If we subtract these three components, the Hall patch, the horizontal, and dislocation, from the values here, we can now end up with the increment because of the strain rate. Okay? And by doing a curve fitting, the values for SLM, ALSI 10mg are shown here. A is 77 and M is 1.18. If we compare it to conventional aluminum alloys from literature, you see different values, a significant difference between these two values, A and M. Or if I plot a graph for the conventional alloys on this graph, we'll have something like this. There is a significant difference between two types of materials, and again, the reason for such kind of difference is the hierarchical microstructure. I looked at the grain structure of the material using EBSC in two different deformation regimes at 1400 per second and 3200 per second. As you see, the formation in the single peak regime resulted in evolution of a discontinuous low angle grain boundary network in the structure, the blue lines in here. By increasing the strain rate, those networks developed, and now we have a well-developed continuous network of low angle grain boundaries. If we analyze that, we see that for the 1400 per second sample, only 30% of the about 30% of the structure is covered by those networks. However, by increasing the strain rate to 3200 per second, now about 60% of the grain structure is low angle grain boundaries. To analyze that, I studied the structure by TEM. Again, since we are deforming the material, we have an increase in the density of dislocations because of dislocation, motion, and evolution of new dislocations. By increasing the strain rate, we'll have more heat in the material. The temperature will rise because of the effect of strain rate. Now, there's another driving force for motion of dislocations. And because of the temperature rise, now the dislocations can rearrange and we can have recovery. That's why, and because of the rearrangement of dislocations, low angle grain boundaries start to develop in the material. At 3200 per second, we have very well developed low angle grain boundaries, and we have the dislocation networks as well. The interaction between dislocations and the features can be seen here. So both silicon precipitates, for example, in this case, and the eutectic silicon walls are playing a significant role on hindering the dislocation and evolution of the dislocation networks. And because the dislocations cannot move easily, they are pinned by the silicon precipitates, as you see here, and also there is another barrier against their movement here. So hexagonal dislocation networks will develop, which is a common kind of dislocation network in FCC materials. And these hexagonal dislocation networks, in presence of temperature, can rearrange, and low angle grain boundaries can evolve in the structure, as you see here. So this is a recovery process. So the initial hardening is related to evolution of or generation of new dislocations. Then we had softening in the material by increasing the strain rate because we had recovery. So far, I was able to explain the initial hardening and softening. Now for the second hardening regime, again, we have generation of new dislocations at high strain rate. So after evolution of low angle grain boundaries, we have nanoscale grains. One of them is shown here, and they're bounded by low angle grain boundaries. Now the formation will continue, and because of the deformation, we have evolution of new dislocations in the structure or inside the grains. That's why we have the second hardening stage. So hierarchical microstructure in SLM, ALS, LMG affected both quasi-static and dynamic loading behavior of the material. Since it's 12:50 or 1:50 your time, I can stop here because I have some other slides on SLM Corax. I prefer to have more interaction with you, so I can stop here. Hopefully in future I can share the results on SLM Corax, which is quite interesting with you. But if you don't mind, I can stop here and answer any questions if there are any questions from you, or I can briefly go through these results. It's up to you. So Dr.
Sure. Thank you. First of all, thank you very much. A very interesting talk. I think in the interest of time and to allow more interactions, perhaps it's better to stop here. So I'm going to basically ask everyone in the audience to please put your question. We have had like a little bit of a confusion. So when you select, you can basically put your question in the chat box, or you can basically put it in the Q&A. If it's in the Q&A, just select all panelists. So with that, I'm gonna. So if you haven't heard your question, I'm gonna basically go with names. Please put your question up there again. So so one question was about slide number 16, and that question is from Ravi. So he asked a question about what is the difference between vertically and horizontally fabricated samples when it comes to grain structures and grain boundaries?
Okay, that's a great question. Sorry, okay, it's not stopping. It's not my fault. So I'm not touching anything. It's just going itself. Let me try to exit the. Okay, that's good. 16. I jumped to 16.
Yes.
So let me start with this slide here. As I mentioned, we can, if we want to fabricate a component, a very simple shape, like this cylindrical shape, we can fabricate it in different directions because we have this freedom in SLM material, or sorry, SLM process. And that's a big question in this context. If we change the geometry, we are changing the thermal history experienced by the material during cooling condition, because we have solidification process in SLM, and that solidification is controlled by the thermal gradient and thermal boundary conditions. If we change the geometry, we are changing those boundary conditions, and as a result, we will have a different grain structure. So here, for example, in the case of horizontal sample, as I mentioned, I didn't want to go through the details of that because there is it's a kind of long and complex topic considering the solidification in the material. But generally, I observed that by changing the geometry from horizontal to vertical, there is a change in the morphology of the structure. So here, more or less, we see an equiaxed cell structure, while in the case of vertical, we see more or less a kind of bimodal or dominated by columnar structure. And we see the same trend in the grain structure. In the case of vertical sample, on the left-hand side, this is vertical, this is horizontal. In the case of vertical, the majority of grains are columnar grains, while in the horizontal sample, we have bimodal structure, and I can say most of the grains are equiaxed. And that is because of the change in the thermal boundary conditions and the thermal history experienced by the material. So that's a general answer to this question. But if you really need to get more details, this is our paper in additive. You can take a look on that paper. I have used a solidification model to elaborate on how this kind of microstructure evolves in the material.
Thank you, Dr. Hadadzadeh. So, Ravi, if you have a follow-up question, please post it there. The next is Pavan was thanking you answering that question in the middle of the presentation. The next question is from Kayvon. He's thanking you for the great presentation, and he is asking a question regarding the dislocations. What is the effect of a high density of dislocation on mechanical properties? How we can tailor the dislocation density via SLM process parameters?
Oh, that's a very good question. Again, dislocations are important in terms of enhancing the mechanical properties because of the dislocation hardening. Again, if I go back to this slide here, because of, as I mentioned, because of the rapid cooling during this process, the dislocations will evolve in the microstructure. And it is very well known that by increasing the density of dislocations, we can increase the strength of the material because the dislocations are interacting with each other. Again, as I mentioned, there is kind of repulsive interaction between them. And in this equation, as you see, if we increase the dislocation density, we can increase the strength increment coming from dislocation. So this is a basic knowledge coming from material science. But the good question here is how we can control the evolution of these dislocations. We observed that changing the wheel direction, again here horizontal and vertical, there was a slight difference in the contribution of dislocations to the strength of the material because we observed a different dislocation density in two samples. Again, that is coming from the thermal history experienced by the material. If there's any way, first of all, SLM, in the SLM process, the cooling rate is very high in nature because of the process, because of the size of the liquid pool that we are dealing with, and that ultra high cooling rate will result in generation of dislocations in nature. But the good question is how we can promote that. If we can find a way to promote cooling rate in the process, probably we can promote dislocation formation in the material. Another way probably is by adding some alloy elements to promote formation of precipitates, because when precipitates are developed in a material, we will have mismatched dislocations between the matrix and precipitates, and that can be another way to tailor the structure. But this is a big question. I mean, we can do a significant research in this field to really address that question.
Thank you. So I think another question by Kayvan, that's basically related to the techniques that you use to get equiaxed grains. Did you check the fatigue behavior of the part with equiaxed in comparison with the columnar one?
No, we didn't do any fatigue tests on the material because of two major reasons. First of all, I was really at that time was really focused on understanding how the quasi-static properties are changing by these features, and it took me a long time to do all of these characterizations and studies and correlations. And second, in our center at that time, we didn't have a good fatigue facility to do the fatigue test, but this is a very good, again, research area. However, there is an argument in the context of fatigue of AM materials. Many people believe that because of the defects in the AM materials, I mean, we still have some defects in the material by controlling all the process parameters, using good feedstock, controlling the environment, we still have the defects in the material. And the fatigue properties, they believe that fatigue properties are controlled by the presence of defects rather than the microstructure. So the controlling mechanism based on their idea, here at the University of Memphis, we have Dr. Fatimi. All of you know him. He's a rock star in the field of fatigue, and he believes, and I guess he's right, I believe he's right, that at the moment, we need to understand the effect of defects on the fatigue performance, and the next step is to study the effect of microstructure on the fatigue performance. So probably in future we can study that as well.
Thank you. Kareem has a question. Perhaps it's related to one of the slides that you showed, number 16. If not, uh, it might be different. But the question is, how the difference in microstructure, vertical versus horizontal, affect the adhesion of the layers?
Well, I guess from what I studied in the optical structure and also SCM, I really did not observe a significant difference in terms of the layers morphology. We go back here. Well, honestly, I didn't quantify their size, but I have some low mag images as well. I didn't report them here. I really did not observe anything in terms of their morphology. And also, there was no major concern regarding their overlap or the interaction between, or if you call it adhesion of different layers. Because during the mechanical test under tensile loading, the properties of the materials were pretty for both horizontal and vertical samples. They were pretty similar. So we didn't observe any evidence of any problems between the layers.
Thank you. I have another question from Mohammed Reza. The question is, in terms of grains that you showed in EBDD maps, what are the pros and cons of having columnar grains? Would you prefer to have a bimodal grain structure instead?
Again, another good question. In general, if we go back to literature on, there's some fundamental studies on the effect of columnar structure on the properties of AM materials, and this columnar structure usually develops because of epitaxial growth. This is kind of classic study in context of welding. And when we have columnar grains, we have a textured material because the grains are developing along a specific direction. Here, for example, we see more red color in the case of vertical sample. Okay, so this red color shows that we have a 001 texture. We have a preferred texture here. By changing the morphology to equiax, we still have a texture material, but less intensity or more random texture. However, I was not able to find any significant effect of such a kind of texture on quasi-static behavior of the material, at least in the case of SLM ALS technology. In general, people, for different materials, they prefer to have a more equiax structure rather than columnar structure, because for the columnar structure, we will have a kind of oriented property, or we have a texture structure that can affect the property in different directions.
Thank you. Pavan has a question before I go to Dr. Hakshinas. There is a follow-up question, actually. Can we eliminate the defects post-processing? And for aluminum alloy, are you using pure aluminum for the process? If no, can't we choose a different grade aluminum with high or low silicon ratio or magnesium based on our calculations?
So to address the first question, there are some post-processing techniques to eliminate the defects, specifically porosities and voids by doing a hot isostatic processing or HIP. We can close the pores by that process, which is very common in the field of powder metallurgy. However, I didn't use that. I didn't use any post-processing to eliminate the pores. To address the second question, the material we used was aluminum silicon, or about 10% silicon and a little bit of magnesium. The reason we use that system, again, as I mentioned, because if we recall the aluminum silicon phase diagram, if I am able to draw it, that composition is close to the eutectic composition. So here is the eutectic composition, silicon, about 11% of silicon. If we decrease the amount of silicon, we are moving to the left, so we will have a larger solidification range, which has detrimental effects on the final component, because there is more tendency for hot tearing, crack formation, and all of these defects. So it's a good idea to move towards this point. That's the first point. And second, magnesium, we can add more magnesium to promote formation of Mg2Si. We didn't do that, but I guess this is a good opportunity if we do that, to promote Mg2Si, because we showed that Mg2Si can play a role on the strength of the material.
Thank you. Dr. Hanos has a question. I think he's going to ask that question himself. And after that, I'll have one follow-up question from Mohammed Reza. Mason, please go ahead.
Sure. Okay, thank you so much, Amir. I would like to start with a big thank you to you for accepting this invitation and providing this wonderful, great talk. I always enjoy these high-quality TM images. It's like some family pictures. I really like them. I have a quick question on strain rate sensitivity, which you showed on additive manufactured aluminum silicon 10 mag. Imagine you run exact same tests on a cast counterpart. Where would you see this cast counterpart sit on that plot that you showed? Is upper or lower?
Okay, so let me go back to plot. I guess you're talking about
number, 31, 32. Yes. Let's assume you run this test on a cast counterpart. Where would
so, considering these values, so let me go back to the previous. Oh, it doesn't work. Okay. Anyway, these values are coming from literature. So 77 and 77 and 1.18. Those are the values that I evaluated based on my own experiments. For conventional cast aluminum alloys, I was able to find the values from literature. If I plot that here, we have a graph something like this, and probably something over here. So there's a difference in terms of the effective strain rates and the strength increment in two cases. I tried to address the effect of hierarchical microstructure on this strength increment in my study. But since I didn't study a cast counterpart systematically, similar to what I did for SLM, ALSI 10MGE alloy, I really cannot answer that question. How the microstructure of a cast material will play a role on such a kind of behavior.
Okay, good. Thank you so much. Thank you, Amir.
Well, I have last question, and it's kind of follow-up perhaps from Mohammed Reza. He's asking, would it be possible to change the texture grain structure using post-processing? For example, can we eliminate the effect of build orientation on the grain structures?
Well, we did a nice study with Dr. Hakshanas on heat treating the samples, and the paper just got published a couple of weeks ago, I guess, in Material Science Engineering A. You can see that. We did heat treatment on the material. By doing heat treatment, different heat treatment, the microstructure really did not change. So I can say if we consider post-processing at a heat treatment procedure, it's not probably, based on my understanding, based on my experience, it's not possible to do that. If we do heap on the sample, I really don't know because I never tried it. Probably if we do hot isostatic pressing on the sample after fabrication, we can alter the structure, or if we somehow cold work the material and heat treat it to have dynamic recrystallization, that's another way to do it. But remember, additive manufacturing is a near net shape. So if we make something to additive manufacturing, it means it's not reasonable to have a post cold working on that. But honestly, I cannot really address this question in details. Sorry about it.
Well, no, thank you. And one last comment from Pawan saying that this is a wonderful presentation and thank you.
Thank you very much. Thank you.
Yeah. Well, if there are no more questions or comments, I would like to thank you again for this wonderful presentation. Hope you stay safe, and we hope to have a chance in the future to host you here at the University of Toledo for an in-person visit.
Thank you very much. I would like to thank you and thanks Dr. Hakshanas for your kind invitation. It was a great pleasure for me, such an honor for me to talk to your community. I'm hoping I see you in future very soon, very soon. Give you a visit in your campus and see you there.
Sure, our pleasure. Thank you so much, Amir, and thank you, everyone.
Thank you. Thanks, everyone.
Thanks.
Good
Bye.
one.